In this video, we'll take a look at an extended error correcting code. What we do is to take an error correcting code like the Hamming code, the 743 Hamming code that we looked at in the previous video, and add one more bit to it, which will be an additional parity bit, and create an extended version of the code. And why we do that, we'll see here in this example. Our original Hamming code that we looked at previously is oftentimes called a single error correcting code, a SEC code. It's capable of detecting and correcting any single error in a code word. This extended code is called a SecDed code. It's also a single error correcting code. That is, it can detect and correct any single error, but the addition of this 8th bit will allow it to detect a double error. It won't be able to correct it, but it can detect that there has been a double error made. That means 2 bits of the code word have been changed, flipped from either a 0 to a 1 or 1 to a 0. So this 8th bit, which is a parity bit, is going to be a parity bit for all of the previous 7 code word bits. So we'll add all those 7 bits together, having filled in the question marks here for the parity bits. We'll add them all together, and if the total is 0, then bit number 8 will be 0 also, because 0 is what you have to add to 0 to get a result of 0, which is what parity bits are supposed to do. If the sum of those 7 bits is 1, then the 8th bit will be 1 also, because that's what you have to add to 1 to get 0. Another way of saying this is just that all these parity bits are just the sum, equal to the sum of the bits for which they are parity bits. Okay. I guess I should have probably said things that way in the previous video also, but at least I'm getting around to doing it this time. Our code word in Hamming's version of code words would look like what we have here. The 8th bit would be at the left-hand end, just in its regular position in the order 1, 2, 3, 4, 5, 6, 7, 8. But the systematic code word, the type of code words that we're interested in for the RF bitbanger, are going to, in the case of an extended code, the additional bit is going to be grouped with all the other bits, which are parity bits, and then up at the end of the code word, and all the message bits are going to be prior to that. Okay, something happens when we add this additional parity bit, this 8th bit. What happens is that if you'll notice here the weights of the words previously, well, let's just go back and look. In the previous Hamming code, our weights, which just means the number of ones in each of these code words, were 3s, 4s, so there's a 7 there. The smallest weight is 3 for a non-zero code word. Of course, for the code word which is 0, the weight is 0, but for all the others, the weight is at least 3. And that's necessary for a code to be a single error detecting code. You've got to have a distance of at least 3 between code words, so that if you make one change due to one error in a code word, you can tell which code word it came from. If code words were had any less weight than this, then that wouldn't be possible. And here's the thing, well, how do you determine the minimum distance from one code word to another, and what does that have to do with the weight? Well, these codes are linear codes, these Hamming codes, and so will the Golay codes be. In other words, they're like vectors, and the sum of any 2 vectors is going to be another vector. The sum of any 2 of these code words is going to be another one of these code words. Okay, so if you're trying to find the distance between 2 code words, the Hamming distance, that's just how many places in the vector they are in disagreement. Okay, how different they are in terms of the components of the vectors. And so since we're in a binary system, every component is either a 0 or a 1, a good way to find the Hamming distance between two code words is to add them together. Looking at these two code words up here, what we would do is look component by component. Both these are zeros, okay. These are zeros. Here's a 1 and here's a 0, so that's one place where they're different. Here's another place where they're different. Here's another place. Here's another place. And here's a place where they're the same. Okay, and so the distance between these two code words is 4. Okay, and we will find that the sum of those two code words is right here, right underneath them. Okay, and it has a weight of 4. Okay, well, every code word in here has some weight, and if you add it to any other code word in here to find out what the Hamming distance between those two code words is, it's going to be another code word in this list. All right, and so if the smallest weight in the set of all these code words is 3, then the minimum possible distance between two code words is 3 in the original Hamming code. Okay, and now back to the extended Hamming code. Well, these are 4s and 8s except for the 0 code word. Okay, and so the minimum distance between any two of these code words now is greater. It's 4. And that's what allows us to detect two errors but not correct them. Because if there have been 2 bits that have been changed, they're going to be a distance of 2 away from not only the code word that they came from, but possibly some other code word, since the minimum distance between code words is 4. So you can't tell which code word they came from. Okay, and so that's what's happening with the code words now, with this additional bit. Just calculating them all, we can see that the minimum weight is 4. Here we have a weight of 8. But the minimum distance between the code words is 4. Okay, so if we set up a systematic code here, then again, just looking at the vectors that are here, we can see a basis for the messages that are in the code words, and therefore for the larger code words. And if we copy those basis vectors one after the other into a matrix, then we get something similar to what we got with the original Hamming code. We see an identity, 4x4 identity matrix on the left, and we see our same matrix B for generating the parity bits, and we just get an additional column here, which is the result of the 8th bit that we've added on to the code words. And so we can generate our systematic code using this matrix. We can generate our code word also more simply by just using our matrix B plus this additional column, which I probably should have identified here. It's not just matrix B, it has this also additional column that we got from our 8th bit. And so as before, we've got a message that has been typed in by the user of this radio, this RF bit banger. That message you can view as a binary number. It's associated with some character that we want to send, like the letter A. And when we multiply it by this matrix B with its additional new column here, we get the parity bits that we need for a code word that has this message now and these parity bits, and all we have to do is glue those together. And this is, again, a very simple process, but now we're able to detect two errors. We can, again, detect and correct one error, but we're going to be able to detect 2 errors. Okay, and we need to set up in order to do that, we need to set up a parity check matrix here, but we do it just like we did before, only we have one additional column now. We've got the column for the parity bit, which is bit number 8, our new one. And again, we just set it up the way we did before. Parity bit 8 is a parity bit for all the previous bits, 1 through 7. And so we're going to select here 1 through all the 7 bits that came before bit 8 and put in 1s in our parity check matrix. That means that we're going to use all of the values from this vector, the received code word, when we do the dot product with this column and add them all up. And that should give us 0 because when we add the 8th parity bit, which is in here, right here, here's our 8th parity bit in this column. When we add, or this row, when we add that 8th parity bit to all the other bits, we should get 0 if nothing bad has happened to the code word. And so here in this case, we're receiving the same code word that was transmitted. No errors have been introduced, and our syndrome, as before, has all zeros in it. Okay, and so we know when we see all zeros there that we've got a code word that does not need to be corrected. Okay, let's go back and put a corruption introduced by the channel that the code word is being transmitted through by adding this error vector to our transmitted code word. We get the received code word, and again we've got an error here, right here. And yes, it's going to be detected as before, though our syndrome does not just say the location of the error with these 3 bits like before. There's also a 1 here corresponding to the 8th bit, which is our new parity bit. And the reason why that's there is that if any single one of these bits changes, then it's no longer going to have a sum. If any one of these message bits or parity bits changes, it's no longer going to have the same sum that it did, and so the parity bit will be wrong. And when you add all these up, you'll get a 1 instead of a 0. Okay, and so we ignore this value. It should be 1. If we have a single error, it should be 1, and the identity, the location of that error is given by the binary number represented by the last 3 bits of the syndrome, just as before. Okay, so it's telling us that message bit 3 is erroneous, and so we correct it. We flip it from a 1, which we have up here, to a 0, and our received message is 1110, the message that was transmitted. Okay, so how about this detection of a double error? What does that look like? Okay, well, let's put another error in here somewhere. Now it's not going to be able to tell that where that error is located, and so you're going to get information here that is useless. It's pointless. Okay, that 4 plus 1 is 5. Well, no, that's not the error bit that was changed. It's 6. But what we have here is a 0 here. Okay, a 0 in this position. But when we have that, and we have something other than 0 in the other 3 positions, we know that there's a double error. Okay, and so as I've set up this spreadsheet to do, it just looks to see that if this is 0 and the other 3 add up to something other than 0, then there's a double error detected, but can't be corrected. We'd need to go to 5, a minimum distance of 5 between code words in order to get to both detect and correct a double error. Okay, so that's the story on extended Hamming code words. We're going to be dealing next with the Golay code, and we'll look at the original Golay code, and then we'll talk about the extended Golay code that is going to be used in the RF Bitbanger and see how that's set up.